A massive steel vessel is moving through darkness, unable to see the sky, coastline, or any satellite above. It is like a blind traveler crossing a maze, guided only by memory, motion, and distant echoes. Dozens of satellites still orbit overhead, continuously sending positioning signals across land and ocean. But when those weak radio waves strike the sea, salt water rapidly absorbs them and makes them disappear. Separated from the sky by only a layer of water, the vessel is cut off from the world's familiar navigation system. By ordinary logic, a vehicle that cannot see the road or receive coordinates should not travel safely over long distances, because on the seafloor, a small error sustained over time can push the journey into an entirely different valley. If the internal system stops tracking movement, the crew gradually loses the answer to the most basic question. Without knowing exactly where they are, every underwater mountain ahead can become a threat. Rising to see the sky may correct the error, but it also breaks the darkness hiding the vessel. Yet these vessels can remain underwater for long periods and cross enormous distances. They carry a kind of mechanical memory, recording every change in direction, acceleration, and tilt. They measure pressure, listen to the ocean, and sometimes recognize the seabed by the shape of its terrain. This is a submarine, a vehicle that must navigate where the sky cannot be seen. Throughout the journey, it must solve one paradox: know where it is without letting the world know. On the surface, humans once navigated by the sun, the stars, coastlines, and distant lighthouses. The earliest submersibles had none of those advantages, so position was estimated from the starting point and heading. A compass showed where the bow pointed, while speed and time helped estimate the distance traveled. This simple method was dead reckoning, but the sea always added invisible motion to the calculation. Currents can push an entire steel hull sideways, even while every instrument reports that it is moving straight. The deeper the vessel dives, the faster light, the horizon, and radio signals leave it behind. Salt water is a wall to many radio waves, but a wide corridor for sound. So the deep sea forced humans to replace eyes with pressure instruments and mechanical ears. Depth measurements from surface ships gradually turned the invisible ocean floor into terrain that could be imagined. A major advance came when gyroscopes helped preserve direction without relying entirely on Earth's magnetic field. Accelerometers then allowed instruments to sense every increase, decrease, or change in the vessel's motion. As maritime, aviation, and control technologies advanced, separate sensors were combined into inertial navigation systems. Submarines capable of staying submerged longer turned self-navigation from a convenience into a condition for survival. Every rise toward the surface to check position interrupted the journey and weakened the advantage of concealment. The new problem required a closed system that could carry its starting point with it for many days. Before diving, the vessel must know its initial position, heading, and velocity as accurately as possible. From that moment, time becomes an adversary because every tiny measurement carries some error. Error rarely appears as one dramatic jump. It usually creeps through a long chain of calculations. That is why a reliable vessel never places complete trust in one sensor or one method. Underwater navigation was born as a continuous comparison between mechanical memory and traces left by the ocean. The earliest solution began with a simple question: which direction had the vessel traveled, and for how long? The bow heading provides an imaginary line, but it is accurate only if the vessel has not been pushed sideways. Speed shows how fast the vessel moves through water, but not necessarily how fast it moves over the seafloor. Time turns speed into distance, making a precise clock an important navigation instrument. Each movement segment is added to the last, creating a route that exists only in records and machines. The problem is that the ocean never stands still, and even a weak current can accumulate into a significant deviation. A magnetic compass can also be affected by metal, electrical equipment, and changes in the surrounding magnetic field. A gyroscope overcomes part of this limit by preserving directional reference through stable rotational motion. It is like a spinning memory, holding the old direction while the entire vessel tilts and turns around it. Meanwhile, a pressure sensor estimates depth by measuring the weight of the water column pressing on the hull. Depth does not reveal horizontal position, but it tells the vessel which layer of the ocean it occupies. Acoustic receivers add another sense, allowing the crew to hear propellers, marine life, and the ocean itself. Bathymetric maps turn seamounts, plains, and trenches into terrain landmarks that can be compared. When conditions permit, the vessel can approach the surface, obtain an external position, and correct its estimate. But that action is only a correction. Once the vessel dives, self-calculation begins again. Every reliable external fix is like placing a lost traveler back onto the correct path through the maze. Yet if it must keep returning to the surface, a submarine can never fully use its ability to remain hidden. The answer is not a perfect compass, but a combination of many imperfect clues. The blind traveler in the maze now remembers footsteps, feels the slope, and listens for echoes from the walls. From these separate tools, a layered navigation architecture begins to form inside the submarine. On a modern submarine, navigation is not the work of one device, but of an entire network of sensors. All data eventually converges in the navigation space, where the estimated position is continuously checked and updated. At the center of this network is the inertial navigation system, commonly shortened to INS. Its motion sensing unit contains gyroscopes and accelerometers arranged to monitor several different axes. 3 rotational axes tell the system whether the vessel is pitching, diving, rolling, or changing heading. Accelerometers monitor forward, sideways, and vertical motion like 3 force-sensitive senses arranged at right angles. The computer receives those tiny movements and adds them over time to reconstruct the vessel's journey. For the calculation to begin correctly, the system needs a trustworthy starting position and initial state of motion. From there, the gyroscopes continuously preserve the vessel's attitude relative to vertical and directional references. The computer must convert forces measured along the hull into motion relative to Earth, even while the vessel is tilted. After accounting for gravity, the remaining acceleration is used to calculate the vessel's new velocity. That velocity is then accumulated over time, producing the next position along an imagined underwater route. The entire process works without sending a question outside or waiting for a reply from a satellite. A separate system tracks depth because an accurate horizontal position is useless if the vessel is in the wrong water layer. A Doppler velocity log can use sound to estimate movement relative to the seabed or the surrounding water. This helps distinguish the vessel's true motion from water simply flowing around it. Digital maps provide the shape of the seafloor, while real sensors check whether the terrain below matches. Passive sonar adds context by listening, but it does not illuminate the darkness ahead. Active sonar can emit a pulse and receive its echo, trading silence for more direct information about the surroundings. Precise clocks keep every measurement synchronized because timing errors can become distance errors. Important sensors often have backups so that one failure does not immediately erase the vessel's sense of direction. The software estimates not only a position, but also the uncertainty expanding around that position. When 2 sources disagree, the system must judge which one is more reliable under current conditions. Humans still verify the result because a reasonable calculation may not fit the terrain or situation. A submarine therefore follows no single guiding star, but the temporary agreement of many senses. To understand INS, first consider the gyroscope, which senses how fast the hull rotates around each axis. From that rotational rate, the computer rebuilds where the bow points and how the hull is tilted. An accelerometer does not measure position directly. It senses the force that shifts a tiny internal mass. The computer must separate real motion from the pull of gravity. When acceleration is accumulated across successive moments, the system obtains a new estimate of velocity. Velocity is then accumulated over time, and the result becomes the position the system believes the vessel occupies. But if the accelerometer is slightly biased, every calculation carries that error farther. Position requires 2 stages of accumulation, so acceleration errors can grow faster than intuition suggests. Temperature, vibration, and tiny manufacturing imperfections must all be calibrated to keep calculations stable. In many modern systems, sensors are fixed directly to the hull while computers process every change in attitude. Optical gyroscopes can measure rotation with light, avoiding many continuously moving mechanical parts. Whatever the design, the goal is to detect tiny rotations before they become large heading errors. Depth is inferred from pressure because more water above the vessel means greater force on the sensor. Temperature and salinity change water density, so converting pressure into depth also requires correction. A Doppler velocity log often sends sound beams downward and observes how the returning frequency changes with motion. That frequency shift allows the computer to estimate relative speed, like hearing a passing vehicle change pitch. When the sound beams lock onto a stable seabed, the system can measure movement relative to the ground. But over very deep water, the bottom may lie beyond range, temporarily removing that important correction source. When it tracks suspended particles instead, the sensor measures velocity relative to moving water, not completely to Earth. This is the difference between speed through water and the speed that moves the vessel across the map. Sound is used because underwater it usually travels farther and more usefully than light or radio waves. With active sonar, the system emits a brief sound pulse and waits for energy reflected from an object or the seabed. The echo's round-trip time, combined with sound speed in water, provides an estimate of distance. Multiple downward beams can reconstruct a wide strip of terrain, revealing slopes, ridges, and valleys. If the measured shape resembles part of the map, the computer can use the match to correct its estimated position. A curved ridge or asymmetric valley can act like a natural fingerprint of the seafloor. Terrain matching does not require a perfect copy. It searches for the best pattern within the expected error range. However, sparse maps or extremely flat terrain provide very few features for reliable recognition. Passive sonar works in the opposite way. It emits nothing and only receives sounds already present in the ocean. Propellers, machinery, waves, and animals create a complex soundscape that replaces a landscape of light. Listening helps reveal the environment, but one sound rarely gives the submarine's own exact position. In civilian or research operations, acoustic beacons with known positions can also support underwater navigation. For a submarine, a safe approach to the surface can provide GPS or another external reference to reset accumulated error. The antenna need not lift the entire vessel from the water, but every surface contact must still be considered carefully. The new fix does not replace INS. It pulls the calculation back toward reality before the vessel dives again. From there, INS, depth, velocity, and terrain continue working together in a new cycle. Data fusion algorithms weigh reliability instead of treating every measurement as an equal truth. Doppler data is strongest when the bottom lock is good, while terrain data is best where maps are detailed and distinctive. If one sensor suddenly disagrees, the crew must decide whether the ocean changed or the instrument is wrong. Underwater position is therefore not always a point. It is a probability region that expands or contracts. INS autonomy has a price. The system cannot always recognize when its own calculations are slowly drifting. No sensor is perfect. Even highly precise equipment suffers from noise, bias, and environmental change. An error too small to notice in seconds can become a significant distance after a long period. The longer the vessel lacks an external reference, the wider the uncertainty and the larger the required safety margin. An unmeasured current can make speed through water and movement across the map differ for hours. When the bottom is too distant or weakly reflective, Doppler lock can fail and INS must carry more responsibility. Rugged terrain creates overlapping echoes, making it harder to identify which surface reflected each signal. Soft mud, marine life, and different water layers can weaken, scatter, or distort sound. Temperature, salinity, and pressure change sound speed, causing acoustic paths to bend instead of traveling straight. Active sonar solves part of the darkness, but its outgoing sound can also be detected by other equipment. Passive sonar preserves silence, but it cannot force a silent rock wall to reveal its distance. Seafloor maps are uneven. Some regions are carefully surveyed, while others rely on sparse or older data. The ocean floor is relatively stable, but sediment, landslides, and geology can still alter local features. A failed sensor may not simply stop. It can produce incorrect values that still appear believable. Redundancy improves safety, but it also increases weight, space, energy demand, maintenance, and complexity. Precise sensors still require calibration because silent drift may begin before any clear warning appears. Magnetic anomalies can weaken magnetic references, especially when they are used as secondary checks. Machinery, propellers, and hull motion create vibration, so inertial equipment must be isolated and compensated carefully. Even environmental sensing must coexist with the requirement to reduce noise from the hidden vessel itself. More sensors create more data, and complexity can conceal an error instead of revealing it. The crew must maintain a mental picture of position while recognizing when the computer appears too confident. The greatest danger is not always losing a signal, but receiving a wrong answer that still looks trustworthy. The journey is therefore imagined as an uncertain corridor, not a perfect thin line. Silence has its own cost. The less the vessel asks the ocean, the more it must trust internal memory. The blind traveler may tap the maze wall to correct direction, but every knock announces his presence. Imagine a reasonable scenario. Ahead lies a rugged seafloor with several passages that look almost identical. Conditions outside make surfacing unfavorable, so the crew must continue relying on internal systems. The last reliable position update lies far behind, while the uncertainty around the route keeps widening. IN still operates normally, but accumulated drift may have pushed the real position away from the centerline. Deep sloping terrain causes Doppler bottom lock to appear only intermittently, interrupting ground speed measurements. The measured depth no longer matches the expected map slope, a small discrepancy that cannot be ignored. A layer of differently heated water bends sound paths, making several echoes weaker and displaced. Passive sonar detects many distant sources, but the soundscape cannot identify which valley branch contains the vessel. On the map, two neighboring valleys look similar, so terrain matching produces several competing possibilities. The crew does not wait for a dramatic alarm. They recognize danger through many small disagreements between sensors. Calm matters more than speed because a rushed decision can inject new error into the entire system. The vessel slows down, increases clearance from terrain, and gives the crew more time to verify the data. The navigation team compares depth history, seabed slope, and earlier velocity to find the most consistent evidence. The checks reveal that an intermittent Doppler lock left a small error in an earlier correction. They now face a choice between remaining silent with uncertain position or using an additional active acoustic measurement. When safe navigation becomes the higher priority, a limited active measurement may be considered to verify terrain. One sound pulse leaves the hull, strikes a ridge ahead, and returns with a shape unlike the other valleys. The measured terrain matches another branch on the map, shifting the estimated position significantly sideways. INS is not discarded. It is pulled to the corrected position and continues from a more reliable reference. Distance from the rock slope is recalculated, and the safe corridor ahead becomes clear again. Silence was briefly traded away, but the vessel avoided continuing on a false assumption. No heroic sensor solved the problem. Success came from understanding the limits of every information source. INS provided continuity. Depth provided context. Doppler measured motion, and echoes confirmed the terrain fingerprint. The scenario reveals that the greatest danger is not darkness, but mistaking an estimate for absolute truth. The vessel leaves the complex terrain without surfacing, yet the crew knows error never truly disappears. Modern systems therefore estimate not only position, but also how quickly uncertainty may be growing. More precise optical gyroscopes reduce drift and extend the time before outside correction is needed. Atomic and quantum sensor research aims to measure inertia more precisely and reduce drift in the future. Improved Doppler instruments can hold measurements more steadily over difficult terrain and provide better velocity data. Increasingly detailed digital maps turn more of the ocean floor from vague emptiness into recognizable terrain. Terrain-aided navigation allows computers to find distinctive features and use them to restrain inertial drift. New survey data also exposes errors in older maps instead of forcing the system to trust outdated terrain. Data fusion software detects disagreements faster, but every result must still be interpreted within environmental context. A good system does not hide uncertainty. It displays it so humans understand the remaining safety margin. Cross-checking procedures prevent one source from silently leading the entire system in the wrong direction. The system also monitors sensor health, searching for abnormal heat, lost lock, strong vibration, or missing data. Simulation lets crews practice recognizing gradual drift before they meet real terrain in darkness. When a suitable opportunity appears, external fixes are still used because autonomy does not mean rejecting references. More stable clocks keep sensors synchronized, improving both inertial calculations and acoustic measurements. Ocean models add information about currents and water layers, helping explain unusual acoustic behavior. Measuring temperature and salinity with depth helps predict where sound will bend, converge, or weaken. Operational philosophy favors passive and internal sensors because they provide information without actively sounding into the sea. Active measurement becomes a tool chosen when needed, not a lamp left on throughout the journey. Computers process enormous data volumes, while humans judge purpose, context, and consequences. Modern underwater navigation is therefore the art of managing uncertainty, not eliminating it. The first misconception is that GPS works everywhere. In reality, seawater blocks satellite signals from deep receivers. Sonar is not underwater GPS because it mainly measures echoes or listens to surrounding sound sources. Passive sonar does not automatically provide exact range to every object. It begins by detecting arriving sound. Submarines do not continuously ping like in films because every transmission changes the acoustic environment around them. INS is not a machine that knows position forever. It is excellent motion memory that still drifts. A compass only shows bow direction. It cannot measure current, ground speed, or global position by itself. Knowing depth is also insufficient because thousands of ocean locations can share the same pressure level. A seafloor map is not a complete photograph of the ocean. Detail depends on how well each region was surveyed. A submarine is not completely blind. It senses motion, pressure, sound, and terrain through non-human senses. The position marker on a display is not direct truth. It is the final result of thousands of measurements and assumptions. The most reliable position usually appears when independent sources agree within an acceptable error range. The goal is not imaginary perfection, but enough accuracy while preserving the required silence. The modern turning point is not louder sound, but smarter use of information already available. More satellites above cannot defeat the wall of water. The solution must work inside the vessel or beneath the sea. More accurate internal sensors extend silence because fewer external corrections are required. Quantum sensors are studied not as magic, but as a way to measure tiny motion with greater stability. Future research also considers natural gravity and magnetic signatures because they require no active transmission. Terrain recognition algorithms compare patterns faster, but their quality still depends on sensors and maps. Deep-sea survey robots also advance navigation because they must return after hours beyond GPS reach. Better digital models allow engineers to test how sensors respond to currents, terrain, and changing water layers. Every well-surveyed seafloor region adds another familiar wall to the invisible maze. Even with advanced technology, the ocean changes and measurements remain limited, so uncertainty never reaches zero. Changing ocean temperatures and currents can alter the sound environment, forcing models to be updated continuously. As software becomes the fusion center, data validation and fault detection matter as much as hardware accuracy. The future belongs not to one perfect sense, but to combining weak clues into a trustworthy picture. The paradox is solved not by seeing everything, but by knowing enough while remaining silent. In that darkness, the submarine still resembles a blind traveler in a maze, but its memory has become far more refined. Every tilt, velocity change, and pressure layer becomes another remembered step inside the machine. It does not need to illuminate the entire ocean because here, silence can matter more than sight. Then the steel vessel disappears into the deep blue, carrying its position like a secret only it truly understands.